So as I think you may be aware, Vanatech has for a bit of time here been working on a life cycle assessment of various vanadium products, starting with vanadium and rebar. We moved that on to a look at vanadium in the VRFB specifically. And so I've got David Santos from Texas A&M here today to present some of that work. I think they're going to give an overview of the previous work on vanadium and rebar, and then really dive into some details on the life cycle assessment of the VRFB. So David, please.
Thank you, John. Yeah, so like John said, we're a team from Texas A&M University in College Station, Texas. And just to give you some context, collectively, our team has memberships in civil engineering, construction science, material science, and chemistry, among others. So we have a wide range of expertise, and some of the stuff we've been working on, if we go to the next slide, John, involves just doing for the entire vanadium industry, or at least most of it, a life cycle assessment. And really the purpose of that is to quantify the benefits of using vanadium in a wide range of sectors, but now really primarily focusing on the carbon and energy savings that can result from using vanadium in these sectors. And so on the right, what I'm showing here and has been mentioned a few times early on, it's that steel is really the largest, it still is, and has historically been the largest sector in vanadium consumption. So that's what I'll focus on first, just to give you a brief overview of some of our findings, and then we'll move on to a more detailed discussion in storage. So we'll go to the next slide here. So just to, and I apologize for the text here in the center, just to give an overview of what a life cycle assessment, what goes into a life cycle assessment. This is the workflow that we've done for the steel side of things. And so we've combined everywhere from structural modeling to machine learning models to predict the composition of certain rebars. And ultimately, we've sort of accumulated an inventory of how much cost in terms of carbon and energy goes into the production of rebar, and then ultimately to the building aspect of it. And then the result of that is we calculate the impact, once again, in terms of carbon and energy associated with using vanadium. And if we go to the next slide, just here are some key results that we've seen, or sorry, that's in the next slide, but this is actually work that has been published. And this graphic here kind of illustrates what we've set out to do. So essentially the comparison that we have made is we've taken a baseline mild steel or vanadium free steel used in construction applications, and we've compared that to a scenario where we're substituting vanadium based rebar, specifically in construction. And so I won't go into detail, but for anybody who's interested in more details, I would encourage you to read our article that's been published in the Royal Society of Chemistry, a family of journals. And the title here is in the top left. And just to show you some of an example of some of the results in the next slide here, we find that globally, these are global numbers, that the amount of savings calculated by using vanadium in the construction industry equates to those equivalent to that of the entire CO2 emissions of the Republic of Philippines. And maybe a little bit more familiar example, those savings that also can be equated to those that you might gain by planting approximately 260 million trees. So a pretty impressive savings, but not overly optimistic either. So this is work that has already been peer reviewed, it's published, and it is blowing up on Twitter and such, being shared pretty frequently. So once again, I encourage everybody to read this if this is of interest to you. And if we go further, or to the next slide here, so as has been reiterated time and time again throughout the presentation, China especially is such an important player in the vanadium industry, both in steel as well as energy storage. And it turns out that the narrative or the background in China is quite interesting as well. And so what we've done is we've taken a historical look, starting from the introduction, or starting from the earthquake, and seeing how policy changes in response to the earthquakes, specifically related to changes in building codes, that initially sort of promoted or really encouraged the use of higher strength rebars with improved seismic performance. And then later in 2018, really mandated their use, how those changes have sort of interrupted the supply and demand, and as well as adjacent markets. So vanadium redox flow batteries. And so I won't go into that because I'd be talking about pricing and projections. But if you're interested in sort of what our perspective is on that, I would encourage you to read the full article, which is coming up in the next two slides here. But just to give you an idea, if we go to the next slide, John, of the amount of sort of the impact that policy changes in China. And I know there's some questions earlier as to whether there might be policy changes in the future related to vanadium redox flow batteries. We find that policy changes can be quite powerful. And so what you're seeing here on the left is basically a change in the relative contribution, or the relative use of low and high grade rebars in construction industry in China from 2005 to 2019. And so what you see here, perhaps the most noticeable one is the dark blue and the light blue. So dark blue was lower grade steel, and after the introduction of these policy changes, that dwindled quite a bit. And then the use of higher grade steel, so like these light blue colors and orange colors here, increased significantly. So that overall drove the intensity of vanadium consumption through the roof. But once again, from a carbon and energy perspective, we find that even though from 2005 to 2019, I believe carbon emissions solely due to industrial processes have increased by about 60%. But in contrast, the savings afforded by microalloying, specifically vanadium microalloying in rebar, has increased by over 2,000%. So to give you some perspective, the savings that we calculated were about 230 million metric tons of CO2 have been saved in China. And that's equivalent to fossil fuels in Ukraine, oil in Indonesia, gas in Canada, and coal in Poland in 2018. So some pretty impressive numbers here that we're excited to share. And if we go to the next slide, looks like there's already some questions on accessing the full publication. So this was recently published in a Cell Press journal under the name of Matter, and the title here is on the left. And once again, we've received a really a good sort of engagement on social media in terms of the metrics of how often this is being viewed and at what rate. So I would encourage anybody to, this one is quite a bit shorter, less dense. So if you're going to start with one, this may be the most easily accessible. So with that, I'll move on to the main focus of today's talk, and that's really performing a very similar analysis, but now with the emphasis being on vanadium redox flow battery systems. And so what we have done is we've collected, this is a meta-analysis. So what that means is that we haven't done fully the entire life cycle analysis as we've done for steel. Instead, we've taken a wide range of publications in information in the literature, and we've agglomerated that and performed a few different projections and analysis from that data, expanding on it further. And so specifically, this compares a vanadium redox flow battery to a lithium ion battery. And once again, the sort of currency that we're focusing on here is carbon impact. So if we go to the next slide, we've kind of tackled this from two different aspects. The first is what's referred to as the cradle to gate process. And really this just focuses on the actual production of the battery. So this includes resource extraction, so vanadium extraction, what it takes to produce the electrolyte, then assemble the battery and essentially deliver it to the consumer, if you will, but does not include the actual use of the battery yet. The second stage that we focused on is what's referred to as the cradle to grave, or the whole life cycle. So this includes everything, all the way from the vanadium extraction to the production of the battery, to the use of the battery, and then ultimately the recycling and end of life processing of the battery as well. And it's important to note here that when we're comparing two different systems, we always refer to a functional unit to make sure that our comparisons are fair and accurate. And in this case, all of the savings are in terms of kilograms of CO2 per 1 megawatt hour of capacity over a 20-year lifetime. So by developing that, or by sort of putting that functional unit in place, it really kind of allows us to make an apples to apples comparison of two different energy storage technologies. So we'll go to the next slide here. The first one focuses on the cradle to gate. And once again, to emphasize, this is really focused on the production of both battery systems. And so what you see here on the left are two case scenarios. The leftmost, highlighted in brown here, considers or does not consider the benefits of not recycling vanadium redox flow, or not recycling any components of both the vanadium redox flow battery as well as the lithium ion battery. And even if we don't consider the recyclability of each system, the vanadium redox flow battery produces approximately 17 kilograms of CO2 for every megawatt hour less than the lithium ion battery. So even at the stages where we aren't considering the benefits of recycling, the vanadium redox flow battery, at least at the production stage, is considerably greater than that of lithium ion battery, at least from the carbon perspective. But very interestingly, and I do want to emphasize here that in the recycling scenario here, we have considered recycling equally for both the vanadium redox flow battery as well as the lithium ion battery. And what you see is that the savings get significantly bigger, at least from the aspect of the savings over lithium ion batteries from vanadium redox flow batteries. So to put some numbers on this, the vanadium redox flow batteries at the production stage is generating about 33 kilograms of CO2 less than a lithium ion battery for every 1 megawatt hour. And so if you're thinking about your own kind of applications, you can basically scale that to the energy capacity of your system, and you can get approximately the total savings from a specific system that you might get. And so naturally, the question that arises here is, why are the savings from vanadium redox flow batteries increasing so much when you consider recycling, considering the fact that we've considered recycling for both systems? And that really comes from the nature of the recyclability of the electrolyte. That's one of the reasons. The fact that you can get so much, essentially at the end of the life cycle of the battery, of the vanadium redox flow battery, a large fraction of that, anywhere maybe between 70 to 90% of the electrolyte, is estimated that you can actually reuse in the next cycle. And so essentially what that means is that in the second application, that quantity of vanadium is close to free in terms of carbon. In other words, its environmental impact is absent. And the second aspect of that is just from the overall arrangement of the vanadium redox flow battery. It's much less energy intensive to recycle than a lithium ion battery. And so collectively, the benefits of recycling are much more pronounced for vanadium redox flow battery systems than they are for lithium ion batteries. So good news all around, at least at the production stage. So if we move on to just a little bit more of a detailed analysis here as to, okay, if we kind of expand the production phase a little bit and really kind of narrow in on what aspects of the production of the battery are really contributing the most in terms of carbon. And it's really the electrolyte production. That's actually a good sign, because that's something that the vanadium industry can be proactive about reducing, and in fact is currently taking some action to
所以我们现在可以采取一些相关的方法。
So what I've shown here on the right are
那在这里右手边我们可以看到
examples of some companies that are,
有些
for
公司，
example, Bushveld and Glencore
比如说 Bushdale 和 Blackdale，
installing some
他们也在进行装
photovoltaic
机，
systems or solar cells in their production
比如
plant.
说在进行一些这个太阳能的生产等等。
Hold on for a second. We're getting one of our translators coming through on this channel. Can we ask that translator to please move over to the translation channel?
Excuse me, Mr. Hilbert, please reset me. I just got offline. It's not so stable. Mr.
Okay.
Hilbert, please reset me as interpreter. Thank you.
Okay, 1 second here, David.
No problem.
While John's fixing that, I'd just like to comment quickly on the recyclability issue. U.S. Vanadium in Hot Springs, Arkansas has recently
好的，我现在来说一下我们的这个回收方面。
verified the recyclability of the vanadium. We've actually refurbished some electrolyte
我们也
and
是在进行
demonstrated
一些
the ability to reuse it.
Wonderful.
And then we actually went
翻新的工作。
put the vanadium, treated it, and put it into our plant and successfully recovered it. So we're going to
我
be
们想
coming
要
out with a
重
white
新
paper
的
on that
来进
subject
行装
shortly
机。
to quantify the results.
那么同时呢，对于结果
Sorry,
来进行量化。
All right. I think they should be in now as a interpreter. Sorry about that. Let's go back to screen share here.
Thank you, John. Yeah, so the takeaway message here is that
这里我们
from the production of the battery, most of the carbon emissions are coming from
那么很多的这个碳的排放
but once again, that's really a vantage point, because
都是一个优势，我们应该去使用这个优势。
We're still getting you translating into the main channel. 215, can you please switch yourself to interpretation? Okay, try again, David. Sorry.
So yeah, the intensity of vanadium production will go down. Therefore, the relative contribution at the manufacturing stages will inevitably go down as well. So those are all good. It's a good position to be, because it's something that we can or that the vanadium industry can actively tackle. So if we go to the next slide here, John. Now we focus on the entire life cycle, and just to reiterate, so this does include the production of the battery. It includes the use of the battery, as well as any components of the battery that need to be replaced during its life cycle. And then as well, it also considers the end of life processing. So actually dismantling the battery from use and then recycling it as well.
All right, David, I'm trying to, this interpreter, she keeps getting knocked off, and then we don't have interpretation. So let me
No worries.
try it again here. Okay, let me try one more thing here.
And I'll just keep talking with more background information here. So, so what you'll see once the slides are up is that the savings from over the entire life cycle of the battery are less than what we saw at the production. Okay, in other words, we're losing some of the savings that we initially had over lithium-ion battery once we start actually using both systems. And there's a few reasons for this. The most important aspect of that is the fact that the round trip efficiency of a vanadium redox flow battery, at least in its current state, is less than the lithium ion battery. So we saw some presentations earlier from the vanadium redox flow battery panelists that the current round trip efficiency for VRFB is around 75%. And a good estimate for lithium ion batteries is about 90%. So what this means is that because the functional unit is the amount of energy that you are ultimately getting from the vanadium redox flow battery, when you take a less efficient system, this means that you have to apply additional electricity in order to get the same electricity out when comparing a less efficient system. And so what we find is that whenever the vanadium redox flow battery and a lithium ion battery are coupled to a green energy source, the penalties associated with that inefficiency are quite small, because the carbon impact of the additional wind electricity that has to be inputted into the system is close to zero. And so when coupled to a wind source, you still get about 30.6 kilograms of CO2 savings over a lithium ion battery for every 1 megawatt hour. Now, the slightly less exciting aspect of that is that if you compare it to at least the current state of the grid, that inefficiency can eventually essentially wash away the savings that we initially started out with during the production phase, and make the carbon emissions from vanadium redox flow batteries throughout the entire life cycle greater than that of lithium ion battery. And so the kind of aspect, this tells this whole story, but something that I want to point out here is that as was discussed earlier when discussing really what the sort of most sort of relevant markets are for vanadium redox flow batteries, is that most systems are planned to be coupled with wind or solar applications. Nobody's building a vanadium redox flow battery system to hook it up to a coal plant, right? The entire premise of this is that trying to make the entire grid greener. And so therefore, in reality, what we might see in actual applications is that these systems are paired to, say, a wind or a solar application. And so in that sense, the vanadium redox flow battery is still saving carbon with respect to a lithium ion battery. And if we go to the next slide here, and so the way that I see it, there's kind of two separate but working in synchrony, two different ways to reduce the use phase of vanadium redox flow batteries. The first is an increased reliance on green energy sources. So as I mentioned earlier, when it's coupled to a green energy source, the inefficiency of the batteries essentially becomes irrelevant. And the second aspect of that is just the optimization of the performance conditions of the battery itself. And so collectively, that will reduce the use phase of the vanadium redox flow battery, kind of reverting those savings back to the massive savings that we get at the production of the batteries as well. So if we go to the next slide, I just want to share some information here. The point that I'm trying to make is that these trends are already in existence. And so what you see here is basically the share of electricity production by source, and this is global data. And the two things that I want to point out is that coal, or sort of the most carbon intensive source, the intensity of a relative contribution of that has been trending down, and solar, oil, and other renewables have been trending upwards. And so that first sort of roadmap toward decarbonization of the use phase that is already in motion and has is pretty momentous as well. And in fact, if we go to the next slide here, what I'm showing is Germany's ambitious and also very promising plan to essentially phase out the non-renewable based energy production. And so just to give you an idea here, so they're looking to phase out nuclear by 2040. And then they estimate that renewables will collectively increase to about 49% of the global energy generation by 2050. So what this means here is that as the energy grid collectively gets greener, then the savings or the incentive to use vanadium redox flow battery also becomes greater. And this is already, once again, a trend that is ongoing and has pretty great momentum. We go to the next slide here, John. The second aspect that I mentioned that will be beneficial, especially when using the battery, is just the optimization performance. And so relative to lithium-ion batteries, vanadium redox flow batteries are still a newer technology. And so it would be unfair for us to expect that they be optimized to the extent that lithium-ion batteries are at the moment. But just some aspects that are currently being improved is the electrolyte conductivity. And so improvements in the electrolyte conductivity will essentially improve the efficiency so that internal resistance will decrease. The energy efficiency, so really that refers to that round trip efficiency that I mentioned earlier, and then as well as the electrolyte concentration. So from a chemist's perspective, we look at what the chemical potential of the vanadium electrolyte is and what is actually being used right now. And there's at least another 40% on tap here. And so there are a few limitations right now as to why that remaining 40% of the energy, or the utilization rate of the electrolyte is not being used, but those are all or sort of challenges that can be tackled and that are currently being tackled. So if we go to the next slide here, and so this slide here is a little bit more information dense. So if this video is available later on, I would suggest spending some time here. But some key takeaways here, I just want to put everything into perspective. The red line here represents the vanadium redox flow battery system, and the teal line represents the lithium-ion battery system. And so what I'm showing here on the x-axis is basically the carbon footprint of each energy storage based on how carbon intensive your grid is. And so what you see is that in the dashed region here, that represents a region where vanadium redox flow batteries throughout their entire life cycle offer or produce less carbon than a lithium-ion battery. And so that currently is capping at about 150 kilograms of CO2 per megawatt hour. And what you see here is that actually encompasses both wind and solar. And so once again, just the takeaway home message here is that when you couple to a wind or solar, it makes sense from a carbon perspective to use a vanadium redox flow battery system. And so currently the EU, the world, United States, and China, their grid electricity mix is represented by the vertical dashed lines here. So we're still a little further away, but as I mentioned, and if we go to the next slide here, that the vanadium redox flow battery is continuously improving, and the two major improvements are coming from the optimization performance. And so that's going to, we're going to reap those benefits during the actual use of the battery, and then from the manufacturing stages. And so really that comes from vanadium producers lowering their carbon intensity. And so what I've done in the next slide here is, and once again, this is quite information dense here. So I would encourage you to spend some time here at a later time. But what we've done here is we've performed some scenarios. So the dark green line essentially represents a use case scenario where the intensity of vanadium production has decreased by 50%. And then the other two scenarios that I've performed here is increasing the efficiency, and then a combination of both decreasing the carbon intensity of vanadium production, as well as an increase in the efficiency of the battery. And to just kind of summarize the take home message here is that there is motivation to both reduce the carbon intensity of vanadium production, but also motivation from a technological aspect to improve the efficiencies of the vanadium redox flow battery. And if those two can be done and are likely, and it is reasonable to assume that they will be done in the near future, then it doesn't matter what the carbon intensity of electricity generation is. In all cases, from a carbon standpoint, it will be beneficial to use a vanadium redox flow battery system over a lithium-ion battery system. And so this is kind of what the future looks like, at least from our perspective, for vanadium redox flow batteries. So if we go to the next slide. So these are just sort of the current savings estimated based on the current vanadium redox flow battery installations. And so I do want to point out that this is what the information that is on Vanatech's website, and it does not consider the ongoing projects, rather large projects that we've already seen in the earlier presentations. And so, but essentially this chart is meant to show the estimated savings that we can get and how they scale with installed capacity. And so the point I want to make here is that with more vanadium, more capacity, then the savings will be larger. And so there should be an incentive to enlarge in the installed capacity, as well as increase the use of vanadium in these systems. And just an estimate, just a quick back of the envelope calculation. So if vanadium redox flow batteries end up making up to 50% of the energy storage market by 2025, then we estimate that the carbon savings will be.
All right, David, I gotta fix this again. Keep talking though.
So we estimate that the carbon savings will be very, very large. And so right now the carbon savings may not appear very impressive, but as mentioned earlier, they really do represent a very small fraction of the vanadium market, at least currently. But we do expect it to grow, and as that market grows, then the carbon savings will also grow. And so, so about 1,500 metric tons of CO2 is what we're estimating, based on some reasonable assumptions by Navigant Energy, as well as Lux Research, McKinsey, and Bloomberg as well. So from some reputable analyst companies there. So if we go to the next slide.
Yeah.
So just go ahead.
Real quick, we're running out of time here.
Okay. This is just some conclusions here. I've already kind of mentioned it, but in their current state, the vanadium redox flow batteries offer significant carbon savings over other storage technologies, but those savings will increase significantly as you decarbonize electricity production, as vanadium suppliers work to reduce the carbon intensity of vanadium extraction, and as the overall performance metrics of the vanadium redox flow battery also increases. And that'll be it for me, John.
Thank you, David. There were several questions that came up during your presentation. Would you mind in this next bit of time just trying to answer some of those online if you could?
Sure, no
if
problem.
we can't answer during the webinar today, we'll try to do some follow-up answering as well.
Yes.
Thank you, David, and thank you to the entire team at Texas A&M. We appreciate it. Great work. All right, so in our last session, we're going to have a presentation from Lefa Communications on some of their marketing and sustainability work for Vanatech and for the VRFB. So, Lefa.
Thank you so much, John. So for those who are not familiar with LIFA already, LIFA is the strategic communications firm. We focus on mining and energy. I'm Gabriela, and this is my colleague Suela. And our presentation for today is